Hey, in this video we'll be talking about 3D transforms. So transformations, generally, they take one piece of data, they modify it in some consistent way. If you apply the same transform to multiple pieces of data, you're going to start seeing a pattern in how that transform affects that data. And we can apply transforms to all sorts of data, from vertex positions to entire geometries and even colors in similar ways. I'm going to focus on 3D positional data because that's the easiest to conceptualize and visualize, but remember that you can do all of this stuff with other types of data as well. So there are three basic transforms I want to discuss. They are scaling, rotation, and translation. And you'll see in the next video why I put them in this order. So these are the three basic tools we have for transforming data, for transforming 3D positions, let's say. So with scaling, we have to provide a scale factor. Usually you give a scale factor in each dimension. So if we're working in 3D, three different scale factors, one for the X dimension, one for Y, one for Z. So what scaling does is it takes your geometry and it changes it to be bigger, or it changes it to be smaller. Scaling can also be done with a negative scale factor, and that's going to flip things. So if I applied a negative scale factor in the vertical dimension to this triangle, then I would end up with the same triangle but inverted. So scaling can be used to do some sort of reflection. It can be used to make things bigger, to enlarge them, and it can make things smaller as well. Rotation is just giving a twist to something. So you rotate a certain amount about a specific axis. So we need to know the angle to rotate, and we need to know the axis upon which to rotate, about which to rotate. So we will take some object. Let's say we take our triangle, and we have to decide what axis we're going to rotate about. If I rotate about this vertical axis here, and I say, okay, rotate it 180 degrees, is going to flip it so that the back side is facing the camera now, or facing me. This is in 3 dimensions. So we could go with other rotations. If you are doing a 2-dimensional rotation, then it's really the same as a 3-dimensional rotation, and you're imagining this axis going through your 2-dimensional shape. And when you rotate about this axis, then you get the rotations that you might be more familiar with in 2 dimensions. And it all just works consistently. We do have to, in this model of rotation, choose a specific axis, the line about which we're rotating, like a top, and we have to choose the angle, the amount of the rotation. And then for translation, we need to be given an amount to move along the different coordinate axes. So let me call them a delta x, a delta y, and a delta z. Translation is simply going to change the position directly. It's going to move an object linearly along the coordinate axes. And you can move along multiple axes at once just by specifying some delta x and delta y at the same time that are non-zero. And you can get diagonal movement that way. You can get curved movement over time if you continually adjust your delta x, delta y, and delta z so that they follow a curve. Alright, so this is simply going to make an object that is somewhere in your coordinate space move to a different part of that coordinate space, but otherwise stay the same. Alright, so we can use these three in combination to do some really interesting effects. If you want to set up, say, like a hierarchical transformation, you have a parent object that has different subcomponents, different parts, child objects, like a character that has arms. You generally want those arms to move with the character when it moves, and for the arms to rotate with the character when it rotates. And if you scaled up and down your character, you'd want those arms to also scale up and scale down. But you can imagine the position of those arms is going to change as well when you scale. So all of these things kind of work together, and we have to apply them carefully. And in the next video, I'm going to show how we're going to do that. We're going to be using a tool called a matrix, and we're going to be applying that to our positional data. And for some of these transforms, you may have heard different ways, you may have dealt with them in the past about how to apply these transforms, specifically rotation, since that one seems to be the most complicated right up front. You might have already worked with rotation using like linear equations to adjust the coordinates, using Euler angles, matrices like we're going to do, and maybe even quaternions. And we'll look at the math in the next video to describe all of these transforms. See you then.